Well, thank you, Dan, for allowing me to be here and to present on transportation infrastructure. As Dan said, I've been involved with some work that's not on the vertical side, as much of this task force is oriented towards, but a lot of the same weather and climate information that is needed for the vertical is also needed for the horizontal. And so I'm going to be talking about a particular project I've been involved with over the last 3 years and some of the design standards that have come out of that project. First, wanted to acknowledge that this is a part of the National Cooperative Highway Research Program. I don't know how many of you are familiar with that, but that's in the National Academies of Science, Engineering, and Medicine, specifically under the Transportation Research Board. And that program is funded primarily by state DOTs, but also by the Federal Highway Administration. And AASHTO, the American Association of State Highway Transportation Officials, is very much involved in that program. I'm the one of the three co-principal investigators on this project with two individuals from ICF who are they are the prime contractor for this, and that's Brenda Dix and Alec Bernstein, who I was pleased to work with, and I'm still working with this as we're trying to wrap up the project. Now, you all know what resilience is, so I don't need to repeat that, but this is the FHWA definition of resilience, and it's a broader topic than climate change, and that's an important aspect of what we've done in this project, and I think what you are doing in this task force. And as I said, I want to focus today more on the horizontal, the transportation aspects of resilience and design standards and where those design standards are housed and how they get updated. So the focus here is on the horizontal rather than the vertical. And again, you don't need a reminder of why resilience is important. Although I do, when I throw out numbers about disasters and the cost of disasters, I think we need to be clear that that's not just about climate change. There are other things that cause stresses related to more resilient infrastructure, in this case, transportation infrastructure. And it also informs how we look at standards and uncertainty in our historical record and how we can use that in improving our design standards and our processes. So I don't take some of these numbers too seriously because there's a lot in them, but there is a strong motivation, and I think we all recognize that for being more resilient in our infrastructure design. Now, this particular project is an NCHRP project, and most of what I'm going to be talking about is related to our findings in that project. And one of them, of course, is a break in the old standards where we assume climate stationarity. But building in new standards that recognize changes, whether they're related to climate or land use or any other types of changes, and also putting in standards a reflection of the uncertainty that we know exists in the historical data, as I just said, as well as in the future. And the two specific outcomes that I'm going to highlight are a resilience design guide. So this is kind of an all-in-one place for transportation designers for how to approach resilience from a general standpoint, and also what specifically needs to be done in various disciplines, whether you're a water resources engineer, a transportation engineer, a structural engineer. This is a general design guide for how you incorporate resilience more strategically. And then in terms of where these design standards are housed, primarily that is in the various AASHTO documents. For those of you who are less familiar with AASHTO, it's a collaboration between state DOTs and the Federal Highway Administration, and is very much respected in terms of the types of standards that they produce. And they're often incorporated into state DOT standards. And so that was where we were targeting our updates, was those standards. Here is just a fun graphic about the kinds of climate changes that we were considering as they impact both roads and bridges, roads on the left and bridges on the right. where we're interested in what changing amounts and intensities of droughts, precipitation, sea level rise, and higher temperatures that we're anticipating and what those effects are on roads. And then similarly on bridges, what changes in precipitation, changes in temperatures that cause less ice or more ice, and how that affects bridges, changes in clearances on bridges because of sea level rise, and additional debris flows, for example, based on higher rates of fire. One thing that you don't see here on the bridge side that I'm going to touch on very briefly is temperature related to expansion and contraction of bridge elements. We did look at that, but did not make any recommendations, and I'll explain why in just a minute there. These are the documents that we focused on. So they're not the ASCE standards that you've been focusing on, ASCE 7 being the one that I'm hearing you talk about the most. But the first 4 of these are AASHTO design standards. The first one's a pavement standard, and we're talking about flooding and temperature there. Then the next 2 are bridge design standards, the LRFD, the load resistance factor design, which is one of the Bibles that AASHTO produces for bridge designs. And there we've recommended incorporations related to sea level rise, flooding, and temperature. And then a complementary guide specification for coastal storms and bridges, where we're focused on sea level rise. And then one that's in draft now, is good timing in a sense that the various committees that are associated with AASHTO that produce a drainage manual that is used by all 50 states and the territories of the US, generally speaking, updates for inland flooding and sea level rise. And we did also focus on 2 Federal Highway Administration documents, one focused on inland flooding, and the second one, Act 25, focused on sea level rise. So I want to go through each of those and give you a flavor for some of the specific changes. Part of this project was to make specific recommendations on these various documents, starting first with the coastal environment and FHWA's Act 25. The updates that we've recommended range from very minor text expansions to increase awareness, to very specific technical information for how designers can incorporate sea level rise, for example. And this slide mentions some of the major sources of information. And we also dealt with the way of getting information out more quickly. As you know, updating standards and reference manuals takes time, and FHWA has this process called technical notes to get information out there quickly. And so we provided some specific information that FHWA could use to update designers on how to incorporate these climate challenges in their technical documents like HEC 25. Also in the coastal environment, I mentioned this highway drainage manual. There's going to be a whole new chapter on resilience and climate changes, and we've provided some suggested text for that. And then with respect to the LRFD bridge design specifications, if you're familiar with them, you know that they have various mandatory provisions that if one adopts these standards, they are required aspects. And then there's also commentary that we've provided. And here's an example in the bridges, the coastal storms spec for AASHTO, where we're very specific on how you incorporate water level, wave crest height, and storm water depths, for example, in bridge designs to prepare them for wave impacts. So that kind of recommendation is being provided to the AASHTO committees that oversee these recommendations, oversee these documents, and the hope is that they will incorporate them or some variation on them. And then with respect to inland flooding, the HEC 17 document is one of FHWA's primary standards for resilience, and the revisions that we've proposed include updating various design standards, and I'll say more specifically about that later, but also introducing some climate risk screening that can be done by a state DOT, and how one would do that so that you can do designs based on an appropriate level of analysis based on the risk level. And also incorporating much more routinely the concept of adaptation over time. We may not think that the expenditure is necessary now, but in 20 years, depending on how the climate parameters change, various adaptive strategies may be cost effective at those times. Similar to the coastal, various improvements for the load resistance factor design have been proposed. There's just a couple of examples on how to consider roughness values as the sea level rises and changes those roughness values, and also changes for design flows based on precipitation runoff and sea level rise. That gets into the compound flooding issues, which I know this committee has been tracking. With respect to pavements, the Bible for AASHTO of pavement design is this mechanistic empirical design pavement guide. And it's a performance-based design guide that uses historical climate data. And we've made specific recommendations on how to incorporate future design. Now, the key thing there, which is relevant to this task force, is what are the sources? NOAA has been discussed as a potential source for some of these future data for pavement design. But we've talked about what sources there could be for those future temperature, that future temperature information, and how to incorporate that into the design process. Now, the thing I mentioned about bridges and temperature expansion that I wanted to just briefly highlight where we did not make any recommendations is when you consider a bridge structure, and Eric may have some interesting comment on this, there are elements that expand and contract, and bridges are designed to accommodate that. And so we looked at whether the change in the maximum and minimum, which is used in design, is expected to change in a significant way that should be reflected in design. And we did a really quick and dirty, this is something that ICF did, to look at what the projected changes in temperature ranges might be. In the lower left-hand corner is the existing historical information, and you can see the color-coded map showing in the north central very large temperature ranges, and going south you see smaller temperature ranges. Is that going to change? And that's what is in the upper left in terms of the moderate emissions, SSP2, and high emissions. And what you see here is that the delta actually is decreasing. And that's because the high temperatures are going up, projected to go up at a different rate than the lower temperatures. But the gap is narrowing, or projected to narrow, in most areas, with exception of California, Lower California, and Southern California, and Arizona, and some areas in the Southeast. So the question that we posed to some of our in-house experts and a panel of experts from the AASHTO side is, how much are these changes relevant for design today? And as you saw on the maps, in most parts of the United States, the change, the delta between the high and the low temperatures is lowering, but we're not going to recommend lowering the design standard because those bridges still need to operate today. But then in some areas, the range is projected to increase, and the maximum increase is 6 degrees. So the question that we posed to the various experts was, is a 6-degree increase in that potential temperature range significant enough to change design or not? And the answer that we got from several people that we discussed this with was no, that's not enough to change design standards. But we're going to be publishing this, we hope. And so that if people want to pick up this analysis and take it a little bit further and they draw a different conclusion at a different time, they could do that. But there aren't any recommendations as a result of our project because of this. So then let me touch briefly on the design guide itself and what it provides to designers of transportation infrastructure. First of all, we try to integrate four resilience design principles, or at least what we've called resilience design principles. And I know these are not new to you either, but one is performance-based design rather than prescriptive design. The challenge there, of course, is that performance-based design demands that designers understand what they're doing a little bit better because it's a little bit less cookbook. You're not told how to do something. You're told what it is you need to accomplish, and you have the flexibility for accomplishing it in various different ways. The second one is to integrate adaptive thinking more routinely, where if we recognize that things are changing over the design life of a road or a bridge, incorporating something sequentially over time as conditions change rather than trying to build it all up front and have the additional cost for that. That leads into the useful life, making sure that we're considering the design risks associated with the entire useful life of the bridge or the roadway. And then maintaining risk tolerance. And this one we could involve with much more discussion. If we say, for example, that a 100-year flood is the appropriate risk, we don't want to just account for future flood risk by saying we're going to now design for the 200-year if the 100-year is currently the right risk level. But we do want to know what the 100-year flood is going to change to over time and maintain that risk tolerance. Now, some might argue, and I might be one of them, that maybe the 100-year flood is insufficient for some assets, and we can look at that. But we don't just adjust the flood risk level because of climate change, is the point here. So those are some of the resilience design principles that this guide leads people to adopt and integrate into the design thinking. We also, in the resilience design guide, took a holistic process of the project development process. Now, the third box where you see preliminary design, final design, and construction is where most of these design standards are housed. But there's a whole process beginning with planning and programming, project scoping, and then operations and maintenance that need to reflect resilience. And if you don't reflect resilience in your programming and planning, you're not going to have sufficient budget to integrate it in the preliminary design and the final design. I want to go through each of these in a little bit more detail, but above you see four what we call overarching concepts that house all of these four design steps, and then the arrow on the bottom is to indicate that there needs to be a feedback process associated with that. So let me go through those in a little bit more detail. In terms of those four overarching procedures or activities, first of all, establish a resilience policy. And there is one that's indicated in the lower left-hand corner of the slide that Colorado has for resilience. You don't have to have a resilience policy statewide, but it sure helps integrate the thinking on resilience. Encouraging collaboration and coordination between various agencies is key. Reviewing the environmental impacts is key. And then one of the themes that we're emphasizing much more significantly in this project is asset management, and how asset management is not just operations and maintenance, but it's the key for the feedback loop in adaptation and in providing feedback for lessons learned that gets back to design and programming and planning. Now, as I mentioned, programming and planning is where the whole process starts from a state transportation level, where you're articulating the system needs and project goals. And here's where you need to screen for the climate risks right from the start. And we've provided in this project a fairly straightforward climate risk screening process that enables states and other transportation agencies to budget upfront for adaptation. Next is the project scoping phase, where the design standards become relevant. You plan for future adaptation pathways. Again, you have to think about this before you get into design. Otherwise, you're overly constrained on what you can do. If you only begin to think about climate and adaptation once you get to design, because the options that you have there are much less flexible. Beyond that, now we get into the design and the construction, where these design standards become more relevant, and we plan for those adaptation features, and we plan for safety during the construction process. And then next we get into operations, monitoring, and maintenance. And part of what we want to emphasize on operations and asset management is tracking climate changes, tracking what the sea level is doing in a coastal community, tracking what temperature is doing, and so that we also house in the asset management system various triggers associated with adaptation plans. Is it time now to move forward on the adaptation? If yes, let's get going. If not, we'll just keep tracking it. And then this operations and maintenance and monitoring, asset management, then feeds back to the programming and planning stage, where we apply lessons learned. So the key, here's that flow chart again that we present for designers, recognizing that anybody in a state transportation or a metropolitan transportation agency generally only resides in one of these boxes. And that's the work that they do and the work that they see. But it's important for them to recognize that it's all linked, and what the message that we're on the soapbox about is that asset management is a tool, is probably the tool to tie it all together. So you include climate information in your asset management. Asset management becomes the way that the planning and programming people tell people involved in this project scoping that we see some significant risks in this project, and you need to begin to scope those risks out. And that's how the design people tell the construction people, this is why we've made this project in this particular fashion. We've allowed for the road to be raised 3 feet in 2060 if the sea level rise is going up, but we're not ready to do that now because the sea level rise hasn't gotten that far. And then from operations and maintenance back to programming and planning, the lessons learned, and asset management is the key to all of that. So let me just finish up by talking about some of the inland flooding standards more specifically, since that's my area of expertise. I'm not a bridge engineer, so I can't comment too deeply on the temperature expansion contraction. But in terms of inland flooding, what we've proposed and provided to AASHTO and the Federal Highway Administration for these 3 documents, the AASHTO Drainage Manual, HEC 17, and the LRFD Bridge Design Guide, is specific risk levels. One of the things that we think is very important to avoid climate resilience paralysis is you don't need to incorporate climate in the same way in all projects. Some projects are very climate sensitive, and they're very important, and so you would have to have a high level of analysis. This is an example of a matrix based on something called a climate change indicator. Greater than 0.8 is a quantitative measure where you're anticipating precipitation changes to be very significant. Less than 0.8 is you're anticipating them to be less significant. And then based on the screening that I briefly mentioned that you do, you can come up with a risk of low, moderate, or high. And based on those 2 parameters, a level of analysis. And you can see on the right-hand side that the level of analysis for the first 2 are just based on historical information. One of them is just based on discharges, which is basically the status quo. And then the second level of analysis is based on more of a statistical measure of how things are likely to vary. And this is just based on historical data. Now, if you're at a higher level of risk, then you can look at projected discharges and confidence limits and higher levels of analysis. So what we're saying to these engineers is many of your projects are going to be low risk level and a low level 1 type of analysis. And so you don't have to be paralyzed by all of the things that you need to do for such a project. but it helps identify those projects where a higher level of analysis is needed. Now, just for example, for many of the elements that are designed for transportation, we use the annual exceedance probability or the return period. And so if the right-hand column is the upper confidence limit that one might use as a check condition if you do need to incorporate climate. So the first row is a 2-year event. The last column says you would look at the 2-year event upper confidence limit. That's what UCL is. As we were going through this, there was some discussion of an alternative check flood, and that's the middle column. If you're designing for a 2-year event and you don't understand the concepts of statistics and you don't know how to get an upper confidence limit, an alternative minimum check condition might be just looking at the next exceedance level probability, which would be a 5-year in this particular case. And you can see going down each of the rows, so you have 2 alternatives for looking at a check flood. For the 100-year, the second row from the bottom, you might look at the next exceedance level, which would be a 200-year, and evaluate conditions then. Or you might look at the 100-year upper confidence limit. Now let's look more specifically at how that might be applied for a culvert design that is for the 0.04, the 4% annual exceedance or 25-year flood. For the check condition for that, for a level 1 analysis, you don't have to do anything unless your existing standards specify a check condition evaluation. If you're at level 2, you would use a check condition, but based on historical information, either the next check flood, the 50-year, the 0.02 or the 2% AEP, or the 4% AEP for the upper confidence level. And you're looking at whether there's impairment at that check condition or not. Level 3 and level 4, you still have your standard historical design condition, which is the 4% AEP, but you're now looking at projected flow information. And this is all laid out in the design guide and the recommendations that we've provided. Now, if you are using confidence limits, the question might arise, well, what confidence limits do I use? And so we've provided some guidance based on the hydrologic service life of the project, the road or the bridge that you're designing. And if you have a longer service life, you have a higher confidence limit that you're looking at. And we've provided some specific guidance for what confidence limits you would be using. So for a bridge that would tend to have a greater than 75-year life, we'd look at the 95% confidence limit. So we estimate the flood associated with that 95% confidence limit and use that as our check condition. If we had something that was a roadway stormwater management facility that had less than a 30-year, we might use a less severe upper confidence limit, still looking at the uncertainty, either the historical uncertainty or the projected uncertainty, and use a smaller upper confidence limit. So that dives a little bit more deeply into how we use the hydrologic service life for an upper confidence limit. And of course, all of this gets into where do we get that data, which is what this task force has been focused on. NOAA Atlas 14 obviously has been a great tool for historical. NOAA Atlas 15 is something that we had been looking forward to, and I don't know what tense to use to describe NOAA Atlas 14 Volume 2 at this point, but there are a lot of regional tools that are already out there that help us with projected precipitation. NOAA Atlas 15 Volume 2 would be a great national tool if and when we get to that point.
So Roger, oh, perfect. Go ahead.
Yeah, I'm wrapping up here. I just wanted to say that our timing in completing this project is auspicious in that it's ready to be published, but we're going through some rewrites based on current administration policies. And it's not clear whether what the time frame for this is. But anyway, yeah, Dan, I'll turn it over to you. That's what I had to offer here.
All right. Thank you, Roger. That was great. I really appreciate it. Questions for Roger? I'd like to take one or two and then move on to Eric because I think this suite of presentations will lead to some discussion, and I want to make sure we have some time for discussion. So, quick question for Roger, technical point, technical question. All right, excellent.